Dr. R. Sugaraj Samuel. He is working as a professor in physics at New College, Chennai. He is also training students for IIT JEE, AIEEE, and BIT SAT. He has more than 16 years experience in both teaching and research. He has published a book titled The Complete Handbook of Bachelor of Electronic Science Practicals, which is prescribed for the syllabus for BSc Electronic Science by University of Madras. He has presented papers in several national and international conferences and has also conducted many training programs and workshops to motivate energetic students. His research areas are ultrasonic, polymers, crystal growth, and photovoltaic systems. He is experienced in both regular classroom teaching and online teaching as well.
Welcome to UGC lecture series in BSc Honours in Physics. We have been discussing about the concepts of the subject electricity and magnetism. In today's lecture, we are going to learn about the measuring instruments of the electrical quantities and the concepts related to the designing of the instruments. Before we start the lecture, let us see the outline of today's lecture. In this session, we are going to see the concepts related to ballistic galvanometer, the potential energy of a current loop, the current and charge sensitivity of ballistic galvanometer, the electromagnetic damping, logarithmic damping, and finally a term called critical damping resistance, CDR. We have all these concepts in store for us to learn. What is a galvanometer? It is an instrument used to find the direction of flow of current. It works on the basis of the torque experienced by a current carrying coil kept in an external magnetic field. These are the well known concepts for us. But as far as the design of this galvanometer is concerned, some technical terms are involved. So, let us start with the basics on which a galvanometer works, and then one by one bring in the terminologies and learn more about the designing aspect. Moving coil galvanometer is a device used for measuring current in a circuit. A moving coil galvanometer works on the principle that the current carrying coil placed in a magnetic field experiences a torque. The expression for the torque is given here. Tau is the torque, which is equal to NIAB sin theta. Each term has got a meaning. N is the number of turns of the coil, I is the current in the coil, A is the area of the coil, B is the magnetic field in which the coil is kept, theta is the angle between the area vector and the magnetic field. We can club these terms together, the NIA, number of turns, current, and area, as the magnetic moment of the coil. Because these are vector quantities, we can write the expression in vector form like this. And this is a diagram which shows how the torque is acting on the coil. When the magnetic field is in the direction from left to right as far as this orientation is concerned, these are the two forces. Actually, the arrow mark is to be shown for this. These forces cancel each other. This is how the force is existing on the four arms of the coil, which is taken in the rectangular shape. So, these two forces cancel each other, and these two forces also cancel, but they are separated by a distance. So, that will produce a couple, or in other words torque, and this torque depends on the quantities which we have seen. The main quantity I would like to highlight here is it depends on the current I here, it depends on the current. So, this equation could be used for finding the current itself in terms of the torque. So, this is the basic idea of the instrument moving coil galvanometer. Why do we have to emphasize that it is a moving coil galvanometer? We have moving magnet galvanometers also. Which is the moving part? As far as the moving coil galvanometer is concerned, the magnets are kept stationary, the coil is allowed to move. In moving magnet galvanometers, coil will be kept stationary, current carrying coil, the magnet will be allowed to move. It is working based on the electromagnetic induction. So, either of the one could be allowed to move with the design. So, we are discussing basically about the moving coil galvanometer, which is an easy one to design. If this torque is counterbalanced by a mechanical spring, then it could be used as an instrument for measuring various quantities, especially current, what I have shown. And what is the meaning of counterbalancing? Here we have a magnetic pole which has got the curved portion inside, that will produce a radial magnetic field. Are you able to see the magnetic field is starting from one point and coming towards it. They all pass through one single point, that is why it is called radial magnetic field. And we have the coil, current carrying coil here. When we have a radial magnetic field and the coil kept inside, the orientation theta value is always 90 degree. It could be easily shown by showing the resolution of the magnetic field, that I do not want to show it here, but in words I am explaining. It is always at 90 degree. So, the advantage is in the expression the theta will become 90, sin 90 will become 1. So, the role of theta is not there in the equation at all. This is one kind of the instrument. It is called the moving coil galvanometer. This is called deflection type. Why it is called deflection type? It will deflect, the coil will deflect. So, this is called deflection. That means it will get deflected, and there is a coil kept inside. This coil, no, it is a counterbalancing coil. This will produce a counter torque. Spiral coil is kept inside, not the current carrying coil, that is shown in red color. There is a spiral coil kept inside, that is called the restoring spring. That spring will counterbalance the torque. So, this needle will come to a resultant position somewhere like this when current is allowed to flow. And on the right hand side I have shown another galvanometer which is called a ballistic galvanometer. What is ballistic galvanometer? What is the typical meaning of the ballistic? Means starting and ending. We have ballistic missiles, right, fired from one point, directly goes and it attacks the target. In between it is not affected. So, it starts from one point and reaches the target. That is why it is called ballistic missile. And in the same way here also, as far as the ballistic galvanometer is concerned, it is allowed to oscillate, start from the middle center when current is flowing. It will purposely oscillate like this, in this manner. It will oscillate the coil. When we have a mirror attached to the coil and light is allowed to fall on the mirror, the light will be deflected. It will show its mark on a scale. So, these kind of measurements are also possible. These are called ballistic instruments. This also has the same principle as that of the deflection type. Only thing is, here the oscillations are allowed to happen and here the oscillation will not be allowed. How does the oscillation come into the picture? We will see one by one, and how the oscillation is needed in some of the cases, why the oscillation is not needed in some of the cases. All that we are going to learn in this lecture. These are the two pictures. This is the deflection type or table type. We call sometimes this as table type galvanometer, which is kept on the table to make measurements, and this is the ballistic. In the case of ballistic, the remaining parts will be covered. Only the mirror, which I have shown, no, the light spot is allowed to fall on the mirror. So there is a window, a glass window is there. So this glass window will allow the reflected light to come out and also allow the light to fall on the mirror that is kept inside. So the two types of galvanometers, how they typically look like, that is also shown here. We will see the concept of the measurement of current and then go ahead with the other designing aspects too. The equation are written as tau is equal to NIAB sin theta for the torque that is produced on the coil due to the magnetic field. By choosing theta 90, we get rid of that because sin 90 is 1, this simple form we have. The coil is attached to a spring which gives a counter torque, tau is equal to C phi. What is C here? C is called the couple per unit twist of the spring that is attached. This phi is the deflection, the angle or the division, whatever it is. At equilibrium, the two torques, the torque due to the magnetic field and the torque due to the coil that is attached to the current carrying coil, the spring, those are equated here, and we keep I alone on the left hand side, current, and rewrite the equation, and this is found to be a constant. I will mark it as a constant here. So current is found to be proportional to the deflection phi. So we call this term as a constant term K. K is the galvanometer constant, or it is called figure of merit of the instrument. What is that K? If you rewrite this equation for K, it is current divided by deflection. If you want to typically explain what it is, if you make the phi, the division or deflection as unity, so how much of current is required for unit deflection, that is called figure of merit. That is also shown here in terms of the other quantities, number of turns, area of the coil, the magnetic field that is present, and of course the couple per unit twist. So what is figure of merit? It is how much of current needed for unit deflection. So it is the trademark of the instrument or an important constant of the instrument, which gives us some information about the sensitivity of the instrument. Figure of merit is not the sensitivity. The inverse of figure of merit is sensitivity. So we will see what is called sensitivity of the instruments. Current sensitivity S of a galvanometer is defined like this. S is the sensitivity. Because it is emphasized as current sensitivity, we have a suffix I here. It is for unit current how much of deflection we are having. So it is the inverse of figure of merit. So it is phi divided by I. If I is made as 1, how much of deflection it is producing? Even for a small current, if it produces some deflection, then the sensitivity is high. So that is the meaning of this. The current sensitivity of a galvanometer can be increased by these steps. These steps are written based on this equation. Increasing the number of turns because it is in the numerator, increasing the magnetic induction B because in the numerator, increasing the area the same way because in the numerator, and decreasing the couple per unit twist of the suspension wire. C is in the denominator, so that has to decrease so that we have a high current sensitivity. What is the meaning of decreasing the couple per unit twist? It has to be a very sensitive spring, very sensitive spring when we use, the current sensitivity will be very high, right. These are the concepts related to sensitivity of galvanometer, especially the current sensitivity. Galvanometer can be converted into an ammeter and also an voltmeter. In the case of galvanometer, the needle will be at the center. If it is measured from one end to the other end, it is ready to measure the current. So, accordingly we have to modify. The same way the galvanometer can be converted into an voltmeter. So, if it is converted into voltmeter, the voltmeter also has a sensitivity. So, let us see what is the voltage sensitivity. The voltage sensitivity of galvanometer is defined as the deflection per unit voltage. S stands for sensitivity, the suffix V we have here is for voltage. So, SV is the voltage sensitivity. For unit voltage, how much of deflection is produced? So, that is called voltage sensitivity. We already have the current sensitivity here, right, phi by I. When we write V is equal to IR, that is what is written here, the Ohm's law. What is phi divided by I? This is current sensitivity. So, current sensitivity divided by the RG. RG here is the resistance of the galvanometer, because galvanometer also has the resistance. So, this RG could be taken as a value. It is available from the data. When we purchase the instrument, the manufacturer would have given what is the RG, what is the resistance of it. In the specification of the instrument, we have these details. And phi by I is already a sensitivity called current sensitivity. So, that is separately shown here. Here we have an interesting factor. An interesting point to note is that increasing the current sensitivity does not necessarily increase the voltage sensitivity. Have a look at this equation, that is why I written the equation. We have a tendency to believe that as we increase the current sensitivity, the voltage sensitivity is also likely to increase, because they are directly related to each other. So, that kind of idea comes to our mind, but it is not actually so. The reason is, read the explanation. When the number of turns N is doubled, the current sensitivity is also doubled, but increasing the number of turns increases the resistance Rg. Hence, the voltage sensitivity remains unchanged when we try to increase the sensitivity by increasing the number of turns, because as the number of turns increase, what will happen? The Rg is also likely to increase, because that will add up to the resistance of the galvanometer itself. So, just by increasing the number of turns, we may not be able to increase the voltage sensitivity, it will remain the same. Maybe the current sensitivity will increase, because there the Rg term does not appear, but voltage sensitivity remains the same even when we change the number of turns. Now, we will go ahead with another concept called the ballistic way of measuring the instrument, and another factor called damping. Why the damping is needed in instruments? See, when there is a torque acting on the needle like this, the needle will get deflected. There is an electromagnetic deflection because of the torque, and there is a counterbalance due to the spring that is attached. So, it will come to a resultant position. While coming like that, what will happen? It will overshoot. It will overshoot and it will have an oscillation, because the counterbalancing will not happen just like that. So, because of the inertia that is present in the system, it will come to a particular value, it will not stop, it will overshoot and oscillate with respect to a particular value. So, how do we use a mechanism so that the deflection is stopped? It has to smoothly undergo the deflection and stop at the point. So, for that the damping mechanism is needed. There are several types of damping mechanisms like mechanical damping, electromagnetic damping, and etc. In mechanical damping, what we will do is, when the deflection is happening, we will have some viscous liquid inside. It will produce a kind of opposition to the movement because of the viscous nature, or we can attach the vanes, wind vanes kind of thing that will move in air, that will oppose the deflection. So, that is the concept of mechanical damping, and electromagnetic damping is also possible. We will see what is electromagnetic damping. In the case of electromagnetic damping, we wind up the coil in which the current is flowing on a material which develops eddy currents. That eddy current will oppose the changing field. So, thus the damping is enhanced. So, in the deflection type of instruments, these kind of dampings are produced so that the overshooting of the galvanometer needle is prevented. That is called dead beat of the galvanometer. Why it is called dead beat? When it comes to a particular position, to show the value, keep it dead, it should not overshoot. So, that is why it is called dead beat of the galvanometer, which is done in several ways. But when we use ballistic galvanometer, it will oscillate because it is having a thread attached. Shall we have a look at the basic ballistic galvanometer that we have seen? See, in this picture we have a thread only attached, maybe a phosphor bronze, some stiff thread, and here we have a very sensitive spring. So, the oscillation is inevitable as far as the ballistic kind of instruments are concerned. The oscillation will continue for some time because the damping is very less in that kind of instruments. So, along with that kind of oscillation, how do we consider the damping that is present? Because the oscillation will not continue forever, it will stop at a point. Maybe the air resistance is only going to be present. When the deflection, first time when we press the key, the deflection will happen and the oscillation will continue, and each time the oscillation will reduce, and we can follow a mechanism to find out the damping that is happening, and accordingly we can find out the correct value of the quantity that we intend to measure. Mainly the ballistic galvanometer mechanism is used for measuring charges, the amount of charge in millicoulomb or microcoulomb, because it is a highly sensitive one, we can use it for measuring the charge. So, charge sensitivity is to be understood. So, let us see what is charge sensitivity. The charge sensitivity of a ballistic galvanometer is defined as the deflection produced for unit charge. But before we first use the ballistic, constant of the galvanometer must be determined. This is usually done by connecting a galvanometer to a known capacitor charged to a known voltage and recording the deflection. The constant K is calculated from the capacitance C, the voltage V, and the deflection D. And I would like to add upon the equation that is shown here. What is the CV? CV is the charge. So, what is the charge required for unit deflection D? That is called the constant of the ballistic galvanometer. The inverse of this is called the charge sensitivity. How the charge sensitivity is measured? How much of deflection is produced for unit charge. So, the charge sensitivity SQ, if you want we can write, it is the deflection produced for unit charge. So, for that we should measure the galvanometer constant of the ballistic galvanometer. I will show you a circuit. That circuit could be used for measuring it. I have shown it for our understanding here. This is the galvanometer and we have a two-way switch and a capacitor. So, what is the use of this switch? When the switch is closed to the lower terminal, the capacitor will get charged, the galvanometer is disconnected. When we throw the switch to the upper terminal, the capacitor will discharge through this galvanometer. So, thus we are able to find out what is the voltage that is charging the capacitor. So, we will be able to denote the V and this is the capacitor C. So, we will be able to find out the charge that is flowing through the galvanometer, and this instrument, this circuit has to be used first, and its inverse is called the charge sensitivity. When oscillation is happening, we have to find out in what way the oscillation is happening, whether it is decreasing with successive oscillation. So, based on that we have a mechanism called the logarithmic decrement calculation. So, that is what I am going to discuss now. The logarithmic decrement delta is used to find the damping ratio of an underdamped system in the time domain. This diagram typically shows how the oscillation is happening with respect to the time domain. We take time on the x axis and the decrease in the amplitude of oscillation is marked, right, and this decrease is happening in the logarithmic way. So, there is a method by which we find the logarithmic decrement. The logarithmic decrement is the natural log of the ratio of the amplitudes of two successive peaks. It is not that we should take the next successive peaks, we can take any number and accordingly this n will vary. When we consider n oscillations and find out the change in the amplitude, so accordingly the n value will vary, and this t is the time period and this is what is the duration. So, this is the duration and this is the time period, this is the number of oscillations that we have calculated. So, using this formula the logarithmic decrement is calculated. Why do we need all this? Because in the case of ballistic galvanometer, the first throw itself is a damped throw. When the throw is happening, this throw itself is damped, because with successive oscillation the oscillation will cease. To find out the actual throw that would have occurred, because that is the actual value we want, because we want to find out the charge. Charge sensitivity is a very important factor as far as the ballistic galvanometer is concerned. So, with the available data, the first throw itself is a damped throw, we would like to negate that by calculating what is the logarithmic decrement and thus try to find out the natural frequency of oscillation of the ballistic galvanometer coil. And I would like to avoid the mathematical steps involved and would like to give only the gist of the calculation in the following manner. The damping ratio is then found from the logarithmic decrement using this mathematical expression. The damping ratio can then be used to find the natural frequency, which is denoted here in angular frequency form omega n, of the vibration of the system from the damped natural frequency. So, this is the damped natural frequency, this is what we will be measuring, and the natural frequency could be found. Once the natural frequency is found, how far the oscillation would have gone in the first throw itself, it would have been a slightly greater value. We will be able to find it out to calculate the actual electrical quantity. So, for that this is used, and ballistic galvanometer also can undergo a kind of damping. When we make a oscillation to cease after the throw, we should not allow it to overshoot to the other side, it has to come to the normal position. So, for that we need to slightly modify the galvanometer circuitry. We have a technical term involved in that, that is what now I am going to explain. A ballistic galvanometer will oscillate if it has not been properly damped. Galvanometers are damped by adding a shunt resistor of just the right amount of resistance in parallel with them. The proper amount of resistance at which the motion just ceases to be oscillatory is called the critical damping resistance, in simply called CDR, and this diagram shows the critical damping. For that, a resistance is to be attached in parallel to the galvanometer. Before we wind up this session, we will see the summary of today's lecture. In this session, we have seen the concepts of ballistic galvanometer, current and charge sensitivity of the measuring instruments, electromagnetic damping, logarithmic damping, and the technical term critical damping resistance. Before we wind up this session, let us test our understanding by answering these questions. Explain the working of a galvanometer. Define current sensitivity and voltage sensitivity of a galvanometer. What is electromagnetic damping? Explain why is it needed. Explain about logarithmic damping. What is CDR? With this, I wind up the entire lecture series for electricity and magnetism topic. Thank you for watching this episode.